here we are. So this is a lab session on regression, and I will take a simulated data set, and by means of this data set we will apply some of the techniques that we have been discussing in our lectures. So first of all, I am calling, well, I'm using MATLAB for this lab session, and in particular I am putting my instructions in a so-called live script. A live script is something that you can find also in RStudio with another name, of course, and in MATLAB, in Python as well. And this is an easy way to have all the commands, and you can then execute just a part of the code. You can change some instruction and then execute again and see what's going to happen, what's going to change. So first of all, let's start with the data. So I'm closing all the windows, I'm clearing all the data, and then I'm calling a script that is called make data, and this script is the ones that's going to create my data set. So I will run this section, all right, and okay, now it's executing. Hopefully, okay. And here the output of this is given by this figure. I think it's very small, so I will just I will enlarge, which is something that can be done because this is interesting, of course. Let's see if okay. So this is my I should say a very complete data set. Then I will work with just a subset of this data. So my idea is to use the data generation process to illustrate you the paradigm we are using when performing regression. So the idea is that we have a joint distribution of x and y, and so each couple of input-output data is a point in this plane, and the idea is that there is underlying a probability density function, and you can see the probability density function, you can see it here, and here it has this strange shape, so you can see that this is something that you will not able to learn by a simple linear function, and of course this was intentional by me to create a data set that was a bit more complex. And if you could sample very much from this joint distribution, then you could have this data set, and this data set explains quite well what's going on. So you have this data, the joint distribution shows this shape, and these data actually were drawn from this joint distribution. And okay, I can also give a closer look. Let's see. Okay, I have to select. There is some lag. Okay, so we can move, and you can see this probability distribution function. What's the meaning of this probability density function? Very simply, it tells you what are the most likely pairs. So where the density function is high, you have a higher probability of sampling an XY pair. And here you can see very well that this high probability region, this high probability region has this shape, and this is something that you can find by means of the conditional expectation. So if you have this joint distribution, you can look for the conditional mean. When you have so many data, as a matter of fact, it is not difficult. You can just take a vertical stripe and an arrow, possibly in a vertical stripe, and compute the sample average of your data, and in the end you will find this curve that is the conditional expectation. This conditional expectation that of course could be computed analytically if you had the joint distribution. This would be obtained by an integral, and it is just in this case this line on the top of the mountain, I could say. And this is our holy grail. So when you are performing regression, the idea is that this red curve would be the best solution. So this is something that I would like to find by means of my methods. It goes without saying that in this lab we are working on XY data, and this of course is a very simple case because the game becomes difficult when you are in more dimensions. So in cases where X belongs to some d-dimensional space with d possibly large, in this case the problem is simple, but we have the advantage that we can have a very nice graphical interpretation. So the data were generated from this joint probability density function. You can look at it from various viewpoints, of course, okay, also from the top, and this is a rather complete data set. So we would like to find the red function. Here it is quite simple. On this data it is quite simple, and for this reason we are not going to work on this data set, but rather, now I'm going to close, I think I can close it. Okay, I will do this way. But rather, we are going to use the data that are published in the link that I sent to you. So this is the file statistical learning theory regression data.mat. Okay, and so now we can go here, hopefully. Okay, live editor. All right. So I run this section, and now I am loading the data, the observation that we are actually working with, and these observations are these ones. So again, I will enlarge to see better. Okay, so this would be a very rich data set. With the one on the left, you wouldn't have problems at all. Okay, as a matter of fact, instead I'm going to work with this data, and if I remember well, these are just let's see, 50 data. Okay, you can see here, these are 50 data. And so our challenge is to be able to get close to this regression function. This is truly the regression function. We would like to get close to this one only on the base of this data. And you can see that this is a real challenge because, as a matter of fact, the real difficult task is to trust these few data that are essential in order to understand that here the curve goes down, and then quite suddenly it goes up. Okay, so it is very easy to have some methods that are going to approximate this curve in some way without looking at this data, but here, for instance, these data are quite important. This will be the difficult part of our lab. Okay, so let's start with some simple techniques. So the first simple technique is k nearest neighbor regression. So I prepared a function that performs k nearest neighbor regression. It is here, Let's see how it works first. All right. I think I should close this one. Okay. I run this section. All right. And okay, here it is. This is what I get. I am using XY data, so just 50 data, and this is the result. You may remember how k-nearest neighbor works. So you are just taking in each point the k-nearest data, where nearest means that the x-coordinate is closest to your x, and then you are taking the average of the y values. And this is the result, which is not bad here, but not good here. But let's look at how many neighbors we took. So here I call the k nearest neighbor regression, and 10 is the number of nearest neighbor. Hopefully you can just type help k and n regr. Okay. And you see that this is k nearest neighbor regression. X and Y are the training data, and X grid is the grid where predictions are to be computed, of course, because I should say where I want to compute my regression function. And as you can see, I took quite fine grid. So I took 200 data. This is a lean space, so it's taking 200 equally spaced points from x equal to 0 to x equal to 3. And given this fine grid, I computed for each point in the grid the k nearest neighbor estimate, and y hat is the output, yk is the number of neighbors. The number of neighbors is important because for this very simple regression method, it controls the bias variance trade-off. So if you take a very large value of k, so you are considering many neighbors, this will smooth the curve, but this will also go to an will also produce a larger bias. On the other hand, you may like to reduce the bias, and this can be done by decreasing the number of neighbors you are considering, but this is going to worsen, to increase your variance. But let's have a look. So here I'm going, sorry, now let's see, all right. So I am performing a nearest neighbor regression with 20 neighbors and with five neighbors, and I'm just plotting these ones. So now we can perform this. All right, this is still busy. You can see here it is written busy, so it is working. It takes some time, and then we can look at the results. Okay, here let's open. Okay, all right, so we still have the previous figure that was with 10 neighbors. Then I can go with just 5 neighbors, and this is this is the black. This is the black. This is the black curve, and you can see that the black curve is somehow better at catching the rise here. Okay, because the bias is lower. But then you have these nasty oscillations. So there is some variance. On the other hand, you can reduce the variance, and this can be done by increasing the number of neighbors, and this happens if you take k equal to 20. This is the blue line, as you can see here, all right? and the blue line you can see here, it's smoother, okay, but well, not particularly satisfactory in order to track the regression line. So I for comparison, I can show you the original regression line. Okay, now it's difficult to have the same scale, but okay, something like that. All right. So the original regression line here, and this is the estimate. So the estimate, if you are not taking the correct value for k, could be somehow poor, of course. All right. So this is k nearest neighbor. Very simple technique. It could be useful if you have many data, because the assumptions you are making are really minimal. Maybe almost no assumption at all, I should say. Okay. Now let's start with some other regression technique. Let's try with polynomial fitting. Okay, in MATLAB we have a function that is polyfit, that is going to fit a polynomial, and then you have polyval that's going to evaluate the polynomials once you have fitted the parameters. So we are just calling the help to see how these functions work. Okay, and then I am going to perform polynomial regression with a quite larger number of polynomials. So I'm going to consider 16 polynomials. So I will start from a polynomial of order 1 and arrive at a polynomial of order 16. But let's see how it works. So we run, we execute this one. I think, well, this might be still useful. Still busy. Okay. Now we are done. Okay. So let's have a look. Okay, let's first have a look at the instructions. So polyfit, you just give x, y, and then n. N is the order of the polynomial. Okay, and you get back the coefficients p of the polynomial. Once you have the coefficients, you can use polyval. Okay, let's see if I can find the help. So this is polyfit. Okay, and here is polyval. Okay, you just use the coefficients you have estimated previously, you give the x's, and then you get y. All right, so this is what we have done with a lot of polynomials. Okay, and let's see, I don't like this one, but I should have somewhere, I saw them. Okay, time to, okay, this is polyval. Don't know, because I have, I don't want, well, I will run again to be sure that, oh, okay, here they are. Okay, I think these are my polynomials. All right, you can see that polynomial of order 1 is a line, and you can see here. Then you have a quadratic function. Here you have a cubic one, and so on. So this is an example of how polynomial regression behaves when you have a data set, and well, it's interesting because you can see that this is clearly insufficient. It's too simple a model. Here it's a bit better, but as you can see, we are not catching these points. The cubic is more flexible. Fourth degree has more chances, but also fifth degree is not bad, as a matter. Here it turns out that sixth degree is quite close to the true one, it seems. Let's see. No, this is the KNN. Okay, I think I don't have. Okay, I don't have the original. All right. Okay, but what does it happen when you increase the complexity? So at the beginning, the bias variance trade-off is in favor of the bias, in the sense that there is a lot of bias, a low variance. When you increase the complexity of the model, the bias is decreasing. So what does it mean? You have many more degrees of freedom. So your model is flexible, and it is flexible enough to follow the what happening in the data. So here you can see that you have a lot of flexibility, but eventually flexibility is too much. You can see here that the model ends up oscillating a lot, and here, but also here in the bottom row, but and maybe also in this other row, you are learning the noise, as I said in my lectures. When you have too many parameters, you end up learning the noise on the data. So these oscillations have nothing, or are not true. They do not reflect something that is real. They just reflect noise. Noise in the data, but okay, that's good. So you just have an idea of what you should expect when you increase your model complexity. Okay, and let's go on. And I prepared something that is similar to polyfit, but instead of using polynomial models, you have a Fourier series. What's a Fourier series? It's just a linear combination of sines and cosines. And here the idea is that you decide the number of harmonics, and the harmonic is a sine cosine pair. And I decide the period. For instance, here we have a range that is from 0 to 3. So I might try with period equal to 3, and this means that you have a constant term, that the first harmonic will be a sine of period 3 together with the cosine of period 3, and then you will double the frequency. So the next one will be a sine of period 1.5 together with the cosine of period 1.5. And exactly as for the polynomial, you have a family of models of increasing complexity. And by the way, these are nested models, meaning that when you consider a certain number of harmonics, you get a model which is a special case of the models that have a larger number of harmonics. So the model with one harmonic is just a special case of the model with two or three harmonics, of course. And it is interesting to see what's going to happen, so we can try. Okay, we just execute. Okay, when I'm done with the lecture, I will upload the video and also the live script, so you can use it if you like MATLAB, of course, but it could be instructive also if you replicate this lab with another platform. Okay, so here we are. I'm trying to gain some space. Here is the help, so Fourier series fit with period t, and once you have the model parameters, then by means of 4-val you can evaluate it. It is just poly fit and poly-val. This is Fourier fit and Fourier val. The idea, I wrote it. It's very simple. This is the result, so we can. I think we can enlarge it. Okay. Hope. Okay. Let's see if I can move it. Okay. All right. There is a lag, time lag. All right. That's good. We have double. All right. So you can see I'm using a sum of sines and cosines, and here it is clear that you have a sinusoid. Okay. Here you are adding higher frequencies, and you go on adding frequencies. It happens that, for instance, this solution is not bad, although this is not the true behavior. But of course, we don't know the true behavior. So here I just showed you at the beginning what is the truth. Maybe it was better I didn't. So this was something that could be revealed at the end of the lab, possibly, but okay, this is another, also knowing it helps you appreciating the challenge and the difficulties of the problem. And so here you can see that as you increase the number of frequencies that enter the Fourier series, you can see that the behavior becomes quite unacceptable. So you, in the end, you are almost interpolating the data. So you have a by the way, you are more flexible than in polynomial case, because each panel, when you move from one panel to the next one, you are adding 2 parameters. So because in my function, the idea is that you decide the number of harmonics, and each harmonic is a sine cosine pair, so you have 2 parameters. So in the end, here you have, I think, 3 parameters, because you have also the constant term, and here you will have this is 32 parameters plus the constant term, so 33 parameters. So here you are becoming quite close to the number of observations that are 50. So you have 33 parameters for 50 data, and you can see that here you are learning the noise quite well. There is also a problem with this solution, because if I take a period equal to 3, I am saying that all the functions in the Fourier expansions are functions that are periodic of period 3, because I just taking a sine and cosine of period 3, then I will have a sine and cosine of period 1.5, but if you are periodic of period 1.5, you are periodic of period 3 as well. All right, and therefore you can see that each function has an initial value that is equal to the final value, which is a constraint that is not motivated at all by the particular problem. So we don't have a prior knowledge that this is going to happen. This could be a good choice if you had to model some natural phenomenon. For instance, if you have to model the seasonal flow of a river, then you make a model on 12 months, and it is reasonable if this is the model of its seasonal flow, that the flow at the beginning of January should be equal to the flow at the end of December. But we don't have this information, so this is not a good choice, it seems. We could try something different. So we just go here, and instead of taking t equal to 3, we could take a longer period. So we would still have a periodic function, but the period would be longer than 3, and so the model would be able to have a different value at the beginning at 0, at x equal to 0, and at the end of my range, that is x equal to 3. So for instance, we could take t equal, well, let's take equal to 9, for instance. There's not a special reason for putting 9, but let's see what happens. So now I'm just executing again, and let's see the result. It seems that we have some problems, so we have some rank deficient, so I will try to comment on this. Okay. Oh. Okay. Okay, still busy, sorry. I'm looking for the results, but it is still busy. Okay. Was done. Okay. Here we are. Let's open the figure. All right. I've lost it. Okay. All right. By the way, we have still the previous function, the previous estimated function. So here you can see that the first one has this shape. The second one, okay, for instance, here this is not bad. Okay. So in this way, I could get some interesting models, while the oscillating one is the previous one with period equal to 3. By using a longer period, you can see that I can get something interesting. But in the end, you end up with the usual problem. So there is too much oscillation, because we are trying to use the degrees of freedom in order to follow noisy data. So we are learning the noise. But at the beginning, for small values, there could be some scope for a model like this. And what I'm doing, I am trying something like a frequency domain approximation. So the idea is that I'm using just some low frequency components. It's like a low pass approximation of my unknown regression function. Okay, so this was another alternative, just to say that there is something more than the polynomial. It is also worth commenting these warnings about rank deficient. What does it mean, rank deficient? You know that when you are performing linear regression, and as a matter of fact, both polynomial regression and the estimation of the Fourier series involve just linear regression after all. When you're performing linear regression, you need the regressor matrix X, capital X, to be full rank. If X, capital X, is full rank, then you are guaranteed that the determinant of X transpose X is different from 0. You theoretically can perform the inverse, or you can solve the normal equations and get your coefficient vector. But as a matter of fact, in the real world, it is not true that the choice is between white and black. So white means that the determinant is different from 0, that you are full rank, and black is that the matrix is not full full rank. But in the real world, there will be cases where you are on the limit of singularity. So you know that full rank means that it doesn't happen that a column of X is a linear combination of two or more other columns, but in the real world it could happen that some of the columns is almost a linear combination of the others, and so here the notion of ill-conditioned problem arises. The, technically speaking, the rank is full, but you are very close to lose your rank, and there are also measures of this ill conditioning, and for instance there is the condition number, and you can measure how close you are to become singular. So this is a warning. It means that computations were performed, but it is warning that we are actually close to be rank deficient. Actually, MATLAB tells also rank deficient, but you can see that there is a tolerance. So the idea is that if you consider this tolerance, you are rank deficient. Technically speaking, you can still perform the inversion, and as you saw, the regression was solved for all the 16 cases. But you should be warned that in some cases the identifiability condition may be satisfied formally, but substantially you are already in a situation where some of the columns of X are more or less are very close to be linear combinations of each other. Okay, in these cases you are advised to simplify your model usually. Okay, there is now another issue that is worth trying. Another point. You remember that when we are going to use as a criterion for model complexity the archaic information criterion of the Mallows CP, you are assuming that an estimate of the variance of the irreducible error is available. During my lecture, I also explained how you could obtain such an estimate. And the key was to use a low bias model. So the idea is that you are using a model with low bias, and usually this can be obtained by using a model that has a sufficiently large number of parameters. So it could even be an over-parameterized model. And by means of this, you can get an unbiased estimate of the noise variance, of the irreducible, of the variance of the irreducible error that can be plugged into Mallows CP criterion or into the archaic criterion. So we are going to put this in practice, and we will use both the polynomial model or the Fourier series in order to assess what is the the variance of the irreducible error. And I'm doing this here, so I'm going to execute this one. Okay, I think it's already done. And here, what I just performed the polynomial fitting with polynomials up to order 12, and 12 is actually too much, so this is not a good model we have already seen. But as I said in my lecture, it is not important that these are good models. They just have to be low bias models. So provided that they are low bias models, then you can get an estimate of sigma square, and once you have your estimate, you can just throw away the model. So you just put it in the basket. No, it doesn't serve you anymore. And so I compute the residuals, and you remember that the unbiased estimate is just the squared norm of the residuals vector, so the sum of squared residuals, divided by the number of parameters. So here we have a polynomial of order k, and so we have to consider that there is, okay, then -1. So the model is of order k, and then you have to, yes. So you have n, which is the number of data, minus k, the order of polynomial, -1 because of the intercept. So the total number of parameters must include the intercept. And I'm going to do a similar thing also for the Fourier series. But let's have a look at the result here. I can enlarge as usual. Okay, this is good. All right. So here you can see that these are the estimate of sigma square. So if I'm using a low order polynomial, you can see that this estimate is sensitive to the order of the polynomial, but from polynomials of order 6 or larger, okay, you can see that the estimate is remarkably stable. And so this estimate, okay, is just the estimate that I could use as an estimate of the variance of the irreducible error. And to see if this works, we can check what's going to happen with the Fourier series. So the Fourier series should give a quite similar result. Okay, so we can expand. All right. Okay. And you can see that the result is reasonably, no, this is not I wanted. Let's see if it is this one. Okay, here it is. So you can see that irrespective of the fact that on the right I have a Fourier series, I use the Fourier series, on the left I used a polynomial, but you can see that in the end the variance is somewhere in between 0.02 and 0.03. Okay, and they give quite a consistent answer. So, and they are different models. It seems that the polynomial does better at arriving early to a reasonable estimate, while the Fourier series gets rid of the bias only starting from here. Okay, but in the end the estimate is quite similar. So this is a demonstration that the method can work. So if you need an estimate, just try an over-parameterized model and then compute the estimate of the variance. Okay. Let's see. I think we should stop here because it's almost 3/4 of an hour. So I would stop for a pause at this point. So I will be willing to accept questions if you have some.